Welcome, everybody. It's my pleasure to introduce tonight's speaker, Dr. Philip Mansfield, who's been waiting patiently there. Philip is a researcher at Stanford University in Kaipak, where he studies galaxies, dark matter, and how the two are related to one another. He received his BS at Carnegie Mellon University and his PhD in astronomy and astrophysics at the University of Chicago. His thesis research focused on understanding the properties and clustering of dark matter halos forming in the cold dark matter scenario. Philip has also made exemplary efforts in education, outreach, and mentoring high school and undergraduate students. He loves teaching and taught high schoolers in Chicago for several years. In his spare time, he likes to swim, bike, and run. And with that, we'll turn it over to Dr. Mansfield. The floor is yours.
Thank you, Marion, and thank you everyone for hosting me today. So I want to start out by imagining that we all went out to a field somewhere in the wilderness. And I think a lot of you would know exactly what we would see if we looked up. So first, you would see a very dense field of stars. And if you went out far enough away from places that had light, you would also see a diffuse band of light across the sky. So this is the Milky Way. This is our galaxy. It's a collection of tens of trillions of stars. And to kind of get a better view of what's happening here, we could focus on this little blob off to the side. So this is the only major galaxy that you can see from the Northern Hemisphere, Andromeda Galaxy. And if you have the Hubble Space Telescope and you point it at it, it looks like this. And you can see that this galaxy looks like a disk that's filled to the brim with stars. There's gas, all these other interesting things in it. This looks very similar to our own Milky Way. So we would sort of be located out in the outskirts of this. And we're looking through it, which is why the Milky Way looks like a giant sort of band of light across the sky. But Andromeda is not the closest galaxy to us. The closest major galaxy, you would have to go to the southern hemisphere to see. It'll be over on the right-hand side of your screen. So this is the Magellanic Cloud. And it's a slightly smaller galaxy that's much, much closer to the Milky Way. And for all intents and purposes, throughout the entirety of human history, the Magellanic Cloud has been stuck in one place. It has not moved. It has been sort of fixed and eternal. And to get a better idea for what is going on with this, we need something that geologists are very fond of, and that's the concept of deep time. So deep time is any amount of time that is so sort of long that humans do not have an intuition for it. Like the amount of time it takes for the Earth to shift and move its plates, these sorts of things. And that's what we need to sort of think about the Magellanic Cloud. I'm going to try to give you a little bit of an intuition for how long these things sort of take. So first off, I want to imagine that you could change the speed of time. You could go back in time and you start clicking backwards and you go thousands of years. You go back through the annals of human civilization. You go back to the Sumerians 5,000 years ago. And you look up and nothing has really changed much in the sky. So you go faster. Now tens of thousands of years are clicking by. And at this point, you kind of feel the climate of the Earth change as an ice age rolls in or out. And you look up at the stars, and you notice that the constellations aren't really in the same place anymore. They've shifted a little bit. The angles between the stars are different than you remember them being. The differences in brightnesses are different. But the LMC is still right there. The Magellanic Cloud hasn't moved. So you start going faster. You start going faster until those gradual ice ages are now just a flickering change in temperature that happens every 100,000 years or so. And at this rate, you soon feel the Earth moving underneath you. After 50 million years, Australia smashes into sort of Southeast Asia. You look back up at the sky and the constellations are totally impossible to see anymore. You don't see anything that you recognize. The stars have all been moving around way too much. You look at the LMC, it's still there, but you can start to see it and turning a little bit. You look at the Milky Way and it becomes apparent to you that what's happening is you're orbiting around the Milky Way. This is happening every 200 million years or so. And so you tick up time faster so that you can actually track these orbits and you start orbiting more and more. After a few orbits, all the planets on the Earth have smashed back together into another Pangea. If you go through another 5 orbits, the Earth becomes uninhabitable. The oxygen has been absorbed into the ground. The sun has become too hot as it goes through its internal fuel. And finally, you start to see the LMC move a little bit across the sky. More orbits go by, more orbits go by. You do maybe another 20 or so. And eventually, the LMC careens into the Milky Way. And I bring this up because I want to get across that we're going to get a little bit familiar with galaxies throughout this talk, but I don't want us to lose sight of the fact that these are really cosmic objects. The time scales, the scale, the distance scales, everything is just incredibly vast. I don't want us to sort of lose that sense of awe for them. It's sort of one of my favorite things about astronomy. Now, this is a talk about how galaxies die. So to talk about how they die, we have to talk about what it even means for them to live. And the way that I like to think about galaxies is that they are essentially breathing objects. They have gases that flow into them and out of them, and those gases are responsible for how that galaxy evolves and changes over time. So you could imagine if you were a biologist, you might have some questions about breathing that you could ask. So what gases does a human breathe in and out? You know, oxygen, nitrogen, carbon dioxide. How are those gases related to life? In this case, you know, our cells need oxygen, so we need to bring that oxygen in. You know, what causes that breathing? In the case of humans, it's our diaphragm. And you can ask the same questions about galaxies. So what gases are flowing through a galaxy? How are those related to the growth and evolution of a galaxy? And what causes them to flow like this? And we'll go and answer those questions one by one. So what I have here is a scale, and we're going to place the different gases that you can see in a galaxy on this scale. So on the left-hand side, you'll have the hottest gases. And on the right-hand side, you'll have the coldest. And also on the left-hand side, you'll have the least dense. On the right-hand side, the most dense. So the least dense thing that you can see in a galaxy is its plasma. So these are ionized particles. So they're atoms that have been broken apart, protons and electrons that are all free floating. And these are spread all throughout the galaxy. You'll find them concentrated around near stars, but in general, they're in a large halo around the galaxy in question. If these can cool down a bit, they might become atomic hydrogen. So those electrons and protons, you know, snap back together once it gets cold enough. And these are concentrated in the center. These are mostly sort of around where the disk is, sort of the stuff that you would see. And if you get even colder, those atoms can fuse together into molecular hydrogen. And you find these mainly in high density clouds. And that molecular hydrogen is really one of the main characters of this story, because it's what forms stars. So on the left, we have the pillars of creation. It's one of the most famous astronomy images of all time. And what these are giant clouds of molecular hydrogen. They're actually evaporating clouds. There's some bright stars above this image that they never show that are evaporating it. And the thing about molecular hydrogen is that it cools really effectively. And as gas cools, it will collapse into smaller and smaller forms. And it continues to cool. And eventually it cools so much that it can collapse into a star. And the amount of molecular hydrogen that a galaxy has is very closely related to the number of stars that it can form. So here's sort of a famous plot of something called the Kennekitt-Schmidt relationship that shows you that the more molecular hydrogen you have on the x-axis, the more stars are formed. And all of these points are either different galaxies or different points within a galaxy. And the relation is quite close. And so together, these gases form a life cycle for galaxies. So what happens is they're surrounded by this very diffuse plasma. And as that plasma cools, it can fall towards the galaxy in the center and eventually become atomic hydrogen. That atomic hydrogen can cool down into molecular hydrogen, and that molecular hydrogen can form stars. And the thing is, though, that once you form stars, you also form really bright stars. You can form supernovae. And supernovae and really bright stars heat up gas, and they can push it back out. So what happens is anytime a lot of gas cools into the galaxy, you form a lot of stars and you push that gas back out. And then once that gas is out, you don't form any more stars, and your bright stars die, you stop exploding supernovae, and now the gas can cool again, it can come back in. And galaxies live their entire lives in a cycle like this, where they're cycling between gas cooling and condensing into the disk and gas being pushed out because too much gas is cooled. And this is what I'm referring to when I say that they breathe. Breathe in, cool the gas, form stars, breathe out, explode in a supernova, push that gas further out. But this is not a complete picture. There's sort of an extra component that's lurking underneath the surface that we haven't talked about, and that's dark matter. So in our current theory of the universe, we believe that most of the mass in the universe is in the form of an invisible collisionless substance known as dark matter. And that this dark matter is collected into massive structures, many, many times the size of a galaxy, called dark matter halos. For time purposes, I won't get into the evidence behind what makes us believe that dark matter is there, other than to say that, like with all scientific theories, the theory of dark matter makes very specific and sometimes very strange predictions about the way that the universe should behave. And so what we do is we try to find as many of those predictions as we can, and we go and test them, whether that's something related to the rotation speed of a galaxy or the way that the very early universe looks. And what we consistently find is that the universe looks in the way that we would predict it would look if dark matter existed. Now, what we're looking at here is an image from a simulation that I made of one of these large structures of dark matter called a dark matter halo. And it's colored so that low density regions like this down here are black, and high density regions like the center over here are white or bright yellow. And so what you can see first off is that there's a big clump. It's roughly spherical, but not entirely. And it gets really, really dense near the center. And probably the second thing that you see is that there's a lot of substructure going on here. There's these little tiny filaments spread all throughout that seem to be feeding towards the dark matter halo. You can see these little tiny other dots, and those are smaller dark matter halos that are surrounding it. And what we believe happens is that galaxies form inside of these dark matter halos. So I've put a little blue oval here that shows you about the size that a galaxy would be relative to this dark matter halo. So the gas gets trapped inside the intense, gravitational pull of the dark matter, and it cools and it condenses into the center into a galaxy. And what this picture means is that the dark matter really tells the galaxies how to live their lives. It tells them where to go, and it tells them when they can grow, because the galaxy can't get any more gas to form stars if the dark matter doesn't attract that gas to it. Can everybody please mute their microphones? Let's do another test. Okay, that sounds great to me. Right. So in order to understand the lives of galaxies, we also have to understand the lives of dark matter halos. So dark matter halos start out in the early universe. And the early universe is really boring. There's no stars, there's no galaxies. There's just sort of this sea of matter, normal matter, dark matter, all of these things. And there are some regions which, just by random chance from a quantum fluctuation, are a little bit more dense than other regions. Maybe just 1 part in 1,000, 1 part in 10,000. But the thing about gravity is that if you have any region which is a little bit more dense than its surroundings, gravity tries to pull it together. And eventually, if you give it enough time, and the universe has nothing but a lot of time, it collapses into a dark matter halo. And so what ends up happening is if you have a really big fluctuation, you can form a really big dark matter halo. But these will be rare. They'll be separated by a lot. And in between them, you'll see smaller dark matter halos. And in between those, you'll see even smaller dark matter halos. Now, what also happens is that these fluctuations don't collapse all at one time. So what will typically happen is there will be some point inside of them that's a little bit more dense than the rest, and that collapses first. And then things start getting attracted to that matter more and more and more over time. And so what happens is that really the shape of this initial quantum thing is what determines how that dark matter halo grows. And in turn is what determines how the galaxy inside of it grows. So I won't have, with that background where we sort of drawn the cartoons of how this works, I want to show you a movie that also illustrates this point. I haven't put it inside of the slideshow because it's quite large, so we'll be sharing it separately. So this is a movie that a collaborator and I made from a simulation of the universe. And it's the same color scheme as before, where it's more yellow, it's more dense, and where it's more red, it's less dense. And we're in the very early universe right now. So you can see that there's sort of a little bit darker over here. Maybe it's a little bit more yellow over here. So what we kind of predict from what I was saying earlier is that this more yellow region is probably going to go and collapse into a dark matter halo. So let's watch what happens. So over time, we start to see that these dense regions are starting to fall together, and we can start to see these little dots showing up, which are the original dense areas. And there are many of them. You can see that there's all these tiny ones because those tiny fluctuations take less time to collapse. And slowly these things are merging together and coming together over time. You can see that over on the side here, it's getting less dense. And now we've started to form our main dark matter halo. You can see its center is right there. And it's accreting matter all from its surroundings. And inside of that matter is even tinier other dark matter halos, which would be hosting their own galaxies. And they fall in. And if you're careful and you watch the orbit of one of them, you'll see that they're losing matter. It's streaming off of them as they're orbiting this thing. And all of this is determined by the initial conditions that are set by sort of the quantum mechanics of the universe. And if you pay attention to the clock on the right-hand side here, you'll see that these orbits are in fact taking billions of years to go through, which is sort of consistent with the story we were telling in the beginning about how long it would take the LMC to orbit the Milky Way. So going back to the slides. There we go. So now that we kind of have an idea of what it means for a galaxy to be alive, let's talk about what it means to kill a galaxy. And there's a lot of ways that you can do this. But let's again get a sense for what this even means. So basically, there are two types of galaxies in the universe. There are galaxies that look like the one on the left, and there are galaxies that look like the one on the right. So the ones on the left are basically disk galaxies. They're blue. They're often shaped like a spiral, although they don't have to be. They have lots of cold gas inside of them. They have young, bright stars, and they look good. You know, they're some of the most beautiful scientific images that are out there. You can fill coffee table books with them. It's how you fund massive telescopes. You show the funders, you know, the pretty pictures of the galaxies, this sort of stuff. But there are other galaxies that don't look like this. You have other ones which are basically red and shaped like an egg. They have essentially no cold gas inside of them. The stars inside of them are old, and they are really ugly. They just look horrible. It's so boring. And so the question is, you know, how are these two things related? Are they just separate? Are some galaxies lucky to be interesting and others unlucky and a little bit dull? And to think about this, we have to think about stars. So what I'm showing here is a diagram that places many different types of stars on it. And the higher up that you go on this diagram, the brighter you are, and the further to the left you go, the hotter you are. And we're going to block out large portions of this chart just because stars don't really spend that much time there, and we're going to focus on this region. So this is the place where most stars spend most of their life. And what happens is as stars get more massive and they go and they get brighter, they also become hotter and bluer. But these hot stars burn really quickly. They burn all their fuel quickly and they die quickly. So blue stars do not live for very long. They die quickly. So the only type of galaxy that can form blue stars and be blue is a galaxy that's actively forming new stars. And stop forming stars, you slowly become redder and redder as your blue stars die off and all you have left are yellow and red ones. So when we look at a picture like this, we know that this is a galaxy which is forming stars, and this is one which stopped a while ago. So these galaxies on the right are formed from these galaxies on the left. And let's talk about how that happens. So one way that you can do this is you can just kind of grow old naturally. So the quantum fluctuation that led to the dark matter halo forming might have a particular shape that means that after the dark matter halo grows a bunch, there's just no more mass left for it to build up. So instead of having a mass that just increases over time, eventually it peters out. And eventually it stops being able to accrete any new gas into the center, and the galaxy just has no more fuel for stars. And it's a bit of a boring way to go, but that's not bad. Method number two is supermassive black holes. So inside of every galaxy, there is or almost every galaxy, there's a supermassive black hole. And what happens is if this black hole is big enough, and if it starts accreting a bunch of gas, it'll shoot out these jets from it, these high energy jets. And what these jets do is they heat up all the gas around the galaxy. And they make it very difficult for more stars to form while those jets have turned on. So if you find yourself in a galaxy where you have one of these giant black holes inside of you, whenever your gas cools down enough, you start feeding the black hole, and the black hole turns on and it stops the star formation. So a lot of galaxies stop forming stars and essentially die because they formed a big black hole in the center, and it doesn't allow them to grow anymore, which is pretty amazing when you think about these things, because they're so much smaller than the galaxy, but they have a really, really large impact on how it evolves over time. And the third way is you just become too big. So if you as a galaxy become very massive, your gravitational pull means that the gas particles around you are just going to be moving really, really fast. If they're moving fast, they have a high temperature and they may not be able to cool effectively and get onto that galaxy in the center. So what I'm showing here is a sort of an image that a professor at University of Chicago took in X-rays of a large clump of galaxies, a galaxy cluster. And it's not really purple, but we can't see X-rays, so we can just say it's whatever color we want it to be. And these things are really blazing beacons of X-rays through the universe. They're just shooting out X-rays in every direction. And that's because the gas there is just so hot that that's sort of the light that it puts out. And this gas, it's very difficult for it to cool. And oftentimes these galaxies will also have incredibly massive black holes, so there will be multiple things going on at once. But there's another way for things to die, a little bit more exciting. And this is related to what we were talking about earlier on with the LMC. So you may die on your own, but you can be killed by another galaxy. So every dark matter halo, and we saw this in the movie, is surrounded by these little tiny, smaller dark matter halos. These are called subhalos. These are pulled in from the surroundings and start orbiting the dark matter halo and being destroyed by its gravitational pull. It pulls the mass right off of them and eventually just rips them to shreds. And we were saying earlier that every dark matter halo has a galaxy inside of it. And what that means is that these subhalos are accompanied by little tiny satellite galaxies. So the LMC, when it's coming in, is coming in with a dark matter halo. And much like that dark matter halo is getting destroyed, those satellite galaxies are also getting destroyed. So let's talk a little bit about what that looks like. So I'm showing you some a real data set. This is from a paper that my old roommate, Nora Schiff, wrote, where she was looking at sort of the sky and looking for the remnants of destroyed galaxies. And it's a little bit hard to see here because, you know, this is real data and real data is messy. So to get a little bit of a better idea of what we're looking at, let's look at a simulation which is trying to show the same thing. So this is from a simulated galaxy. And here it's a little bit cleaner. It doesn't have any of the artifacts. And you can see that there's a lot of features that look like this. You see, I should mention that astronomers often flip the, invert the brightness so that bright objects are black and things that are dim are white, because it's easier to see black on white than it is to see white on black. So the black means that it's brighter, not dimmer. So you can see sort of a bright center and then these little tails off in either direction. So those are the tails that you form by sort of losing your stars as you're orbiting sort of your central galaxy. But the great thing about simulations, and the thing that I really like about simulations, is that we're not constrained to look at them in the way that they would look in the real universe. So here's another view that I think is a little bit more compelling in terms of this. So this is also from a simulation. It's very similar to the others, but the author of that simulation, Adrian Price Whelan, has made these objects much brighter so they stand out, just so you can see them. And then has also colored them in a bunch of different wacky colors. So pink and blue and green and orange and all this stuff. And this is showing a typical, what is happening around a typical galaxy. And what we see is that it is filled to the brim with and disrupted smaller galaxies. Almost all throughout the halo, it's just chock full of them. And many of these we can see. We have a huge catalog of these around our own galaxy, the Milky Way. And there's kind of two perspectives you could take on this. If, let's say you were a galaxy. You could imagine that from a Galaxy's perspective, this is basically like a horror movie. Like you just show up to the neighborhood and suddenly you just see all these like destroyed galaxies sort of orbiting this much larger object. It's like a monster that's coming for you. But another way to think about it, maybe a bit more peaceful, is that these galaxies are ultimately contributing their stars to something larger, to this larger galaxy that they're orbiting. In that sense, it's kind of like this beautiful way to go. And I think maybe whether you see violence here or something, you know, where everyone's contributing together kind of depends on your life philosophy. I think I see the more violent version as being more intuitive. Now, the thing that's nice about them is that you can use these objects to understand the dark matter halo. So what I've drawn here is a cartoon of two different potential dark matter halos that you could have. And so they have different shapes from one another. And so what happens is these stellar streams here, the way that they disrupt is based off of the shape of the dark matter underneath them, how strong the dark matter's gravitational pull is, all of these different things. So what ends up happening is if you change the shape of the dark matter halo, you'll see these different curvatures to the stream. So here I've kind of made a little bit of a cartoon. And what you can do is you can take a large collection of these streams that you measure, and you can piece back together what the dark matter halo looks like underneath those streams, even though you can't see the dark matter itself. And so this is a very active topic of research that people are really interested in, because we want to understand everything that we can about the dark matter halo, because dark matter is so mysterious and we know so little about it, and it's so hard to observe. Now, what some of you may have noticed about the structure of this talk is that moving from older and older ideas to more and more cutting edge ones. And we're going to talk about sort of the most cutting edge of these ideas next. And that's that we can use these galaxies not just to understand the shape of dark matter, but maybe to understand what dark matter is, one of the biggest mysteries in astronomy. So the most common theory of dark matter is that dark matter is some type of fundamental particle that's been there since the early universe that doesn't interact with itself. If you have two dark matter particles that are colliding towards one another, they'll just pass right on through. And we can sort of talk a bit about why that happens, but that's sort of the basic theory. And what we would really like is to find some evidence that there is an interaction between them. And the reason that we would like that is because if there's an interaction between them, that means that if we understand that interaction, we understand some of the physics of that dark matter particle. And the thing is that if you change the physics of the dark matter particle, you change the way that a dark matter halo looks. So what this plot is showing is the density of a dark matter halo relative to the distance from its center. So this black line is showing, kind of the standard view that people have of what these things look like. And what happens is as you get closer to the center, the density just goes up and up and up and up and up, and you kind of look like this. So you have, a less dense exterior, then you get more dense here, and then you get more dense in here. But if you change the way that dark matter interacts, if you say, well, actually, let's hypothesize that I do know some of the physics here, you can reduce the density in the center. So instead of sort of having this really dense core, it's much less dense in here. And so this is great. This gives us something that we can sink our teeth into, because now we've made a testable prediction about the universe. We've said, if the physics of this thing works this way, dark matter halos should look like this on the left. And if it works the other way, it should look like these dark matter halos, on the right. And if there is some interaction, it should look like these ones on the left. And so we can run simulations of these two different things, and it results in dark matter halos that look very different. So on the left here, you're seeing another dark matter simulation. This paper used a different color scale than me. So the green is underdense regions, and then sort of the orange to red to purple to white is denser and denser regions. So you can see in this simulation, which is normal dark matter, that you kind of have this oblong shaped egg thing, and that there's this huge swarm of smaller dark matter halos, each of which could potentially host a galaxy. But if you instead add this physics in, you see that the dark matter halo gets rounder, and that there are fewer little satellites floating around. And the reason is that when you've changed that physics, you've both A, made it harder to form small dark matter halos, and B, made it easier for them to get destroyed by a dark matter halo that they're orbiting. And in fact, we can use observations to rule out a model as extreme as the one that's being shown here. So we know that the dark matter can't interact in this way, but it could interact in this way. So you can still have a dark matter that interacts with itself in a way that is still interesting to physicists. And it can look awfully similar to sort of standard dark matter. And so the question becomes, if you want to be able to tell the difference between this model and this one, you have to start being very careful about precision. You have to be careful about your simulations, about the things that you measure. And the more careful you are, the more types of dark matter you could either rule out or prove the existence of. So what I'm going to do sort of briefly is just talk about some of the avenues that people at Stanford are using to sort of learn more about the nature of dark matter with these types of satellites. And I'm going to show a bunch of plots. You don't have to read any of those plots. Each one of those just represents a paper which has either been written or is going to be written in the future. It's in the process of it. And for fun, I've color-coded it based off of who wrote it. So the ones that I've written or will be writing are in blue. Ones that are written by my students or people that I'm closely collaborating are in pink. And ones that I'm not related to but just love are in red. So one way you could imagine pushing this forward is just by running more and better simulations. You could put more particles inside of the simulation. You could simulate different dark matter halos. And this is a direction that we're absolutely moving in. And we have a new simulation suite called the Symphony Suite that is going to really push the boundaries in this direction. You can imagine trying to understand and fix problems in the simulations, identify them, and then sort of try to see if those issues can be fixed, because your ability to predict things about the universe is only as good as your ability to use simulations to make those predictions in the first place. You could try to understand what is happening to those stellar streams, to those stars, as the halos inside of them are disrupting. How closely are those two things connected, and how can you back out information about one from the other? You could do sort of the thing that we talked about on the previous slide. You could see how changing the dark matter physics could go and affect the properties of halos. And you could create new statistics to study. You could say, well, we really need to not just sort of look at the number of dots that we have here. We need to think more about how they're related, because that can change between different types of dark matter. You could ask about how galaxies are affecting these halos, not just the dark matter. You could ask questions about how galaxies and halos are related before they disrupt, which will give you information about how to model this in the first place. And then you could also ask questions about how biased our observations are. When we observe an object like this, sort of how reliable is that in telling us what an average object like that looks like in the rest of the universe? And so I mentioned earlier that one of my favorite things about astronomy was the scale of the objects that we were talking about. And my favorite thing about astronomy, though, is this, which is that despite the incredible scale of these things, sort of the incredible amounts of time, the scales and all this sort of stuff, the same scientific method that we can use to understand, say, a vaccine still works. As long as what we do is we come up with a model, we make predictions with that model, and we test them. So that's my favorite thing about being an astronomer. So on that note, I believe that my time has come to a close. So I would just like to say thank you again for inviting me, and I'd be happy to answer any questions that you have.
Hi, this is Ken Lum. I have a question about, you mentioned, you're talking about dark matter interactions and how the kinds of interactions would influence the kind of model result that that you would obtain. What kind of interactions are you talking about? I presume that most dark matter interactions would be gravitational, so they would be attractive. But are there other interactions that you could build into the model?
Absolutely. So, and first off, your initial intuition is completely correct. So any dark matter model that you could ever write has one ultimate commandment that you can never break, which is that the main way that dark matter interacts with the rest of the universe is through gravity, just like everything else. And but everything else has to be weaker. Any interactions that you have to be much weaker than gravity. So gravity is sort of the lodestar for anything that you do here. What you can do beyond that is you can make them interact in ways that are kind of similar to normal matter. So when you say put your hand on a table, the reason that your hand doesn't go through that table is because there's an electromagnetic repulsion between the atoms in your hand and the atoms in the table. So one thing that you could imagine doing with dark matter is you could imagine giving it, say, a force that looks like electromagnetism, but is really, really weak. Now, it turns out that something like this has to be incredibly weak to not be sort of detected. And people usually don't talk about models like that, but that's sort of an example. So it could actually be like things that are in our real life. What people usually talk about, though, with these interactions is things that are a little bit stranger, that have a little bit less, it's less intuitive for everyday life. And these are interactions through the weak nuclear force. So this is a force which is very hard to explain. I have never really succeeded in doing it, but it's the sort of force that's responsible for certain types of nuclear reactions. It's responsible for things like the neutrino. And it turns out that if the dark matter particle can experience a little bit of this force, then it ends up having a lot of properties that are very nice, that make a lot of sense for the way that the universe works. And what this will often mean is that if two dark matter particles are coming towards one another, there's a very small chance that they might either bounce off of one another or destroy one another and create some photons or something like this. So usually when we talk about interactions, that's what we're talking about. But there's this whole zoo of different things you could do. Another example is that you could have them be, quantum mechanical waves that are just enormous, that are, half the size of a galaxy, and they'll superimpose and all this wacky stuff. It's really, really cool. And actually, I think in May, one of the world experts on that type of dark matter, Chandra Prescott-Weinstein, will be giving a talk. And I just want to plug that because she is, I think, literally the best public speaker in our entire field. So if you can go to that, I highly recommend that you do. Does that answer your question?
Well, it partially answers my question, but you didn't exactly enumerate the kinds of interactions, aside from saying that there's a possible repulsive reaction, kind of like the electromagnetic repulsion of the outer shell electrons between, say, my hand and the table.
Right.
But there is a postulation of a weak repulsive interaction, I suppose, that one could introduce into your dark matter model that would be much weaker than gravity itself.
Right.
And then you get into other kinds of interactions that you sort of glossed over, which is weirdo interactions, which are based upon the weak nuclear force, which may be a little hard to fully understand. I suppose there's a large statistical element to that because that's what weak interactions are all about.
Right.
But as you say, that may be a little hard to explain in the current circumstance.
Right. And I'll also be upfront about this, which is that my expertise is not in these interactions. So,
okay.
The people who study these interactions specifically are really, really good at it. And you have to have a really solid knowledge of particle physics. And actually, if we go back to this plot here, just because I want to be open about the things that I'm not sort of a total expert on, you'll notice that when we talk about these dark matter interactions, I'm not sort of involved in these papers. So, while I do just want to make it clear when we're sort of talking about things that, while I know sort of what an average physicist knows, I'm not sort of a world expert in those types of interactions. But I will say that there's an incredibly vast zoo of these sorts of things. People who do this will often put up slides in their talks which show every single model that they can think of. And the slides are just jam-packed with all these different wacky names. Like, I think I've seen some that have hundreds. And again, to go back to Chanda Prescott-Weinstein, she has a slide that she shows every time. And it's just, it drives you insane to look at. It's like glimpsing madness to see all the different models that you can come up with.
So basically, these interactions are are hypothesized new physics in the interactions of matter. Then
absolutely,
right.
Absolutely, right. And this is why there's such a holy grail for us, because the current state of particle physics is that there's something called the standard model that predicts the properties of all the observed particles that we see out there. But our theory of dark matter really, really predicts that there should be at least one new fundamental particle out there, which means that there's something that the standard model doesn't predict well, which means that there has to be physics that we're not familiar with that's leading to sort of this weird particle that's out there. So people really want to find it. Mm-hmm.
So these interactions are not in the category of the interactions that are postulated, that are already cataloged in the standard model.
Some of them. Some of them are. So you can do two things. You can do a number of things that you can change about the standard model. So one is that you can hypothesize new interactions, and then the other is that you can hypothesize new particles. And these two things are related to one another. You know, if you have new interactions, you often end up getting new particles. But the most popular theory of dark matter, it kind of has a weird name. So they're called WIMPs, weakly interacting massive particles. And here you don't hypothesize a new force. You say, we're going to use the old forces and we're going to use the weak nuclear force as our force that they can interact with. Okay. And we're going to say that it's a massive particle that interacts like this. So it's not like a neutrino, which interacts through the weak nuclear force, but is very low in terms of mass. And so this is the thing that people really like. And they like it because historically, before we had started testing for the existence of these things, it made some nice predictions about the early universe. But people have put sort of detectors underneath mountains, you know, deep in coal mines, this sort of stuff, that would have been able to find the most intuitive versions of the WIMP, and they haven't been able to yet. So as those experiments have gone on, people have started saying, well, let's branch out and look for wackier types of physics. And the thing is that there are a lot of compelling arguments that you can make for ways that you could extend the standard model and you could extend physics. One of the most popular is something called an axion. You know, this is one of those things where it's essentially a quantum mechanical wave that is, sorry, I hadn't realized that my camera was off this whole time. It's essentially a quantum mechanical wave that's like a fraction of the size of a halo or a galaxy or something like this. And that has a lot of interesting properties, and you can also test for it in the lab as well in various ways. So the goal of this is always to come up with a new form of dark matter that makes a testable prediction, and then you try to test it either in a lab or astrophysically by sort of looking for changes from the standard from what you see with standard dark matter.
Do all these interactive models, you mentioned that most of them do not require the postulation of a new force, but maybe some of them do. I don't know.
Yeah. So I remember the first week that I was in grad school, we had a talk from somebody who had postulated this. So her name is Lisa Randall. She's a professor at Harvard.
Oh, yeah.
And so she had come up with a theory of dark matter where it interacted essentially like electromagnetism. And what would happen is, you know, in the same way that you form disks out of normal matter, that happens almost entirely through electromagnetic interactions. You would form disks of dark matter also. So you would form a dark matter halo, but some of it would form a disk. You know, what would happen is that, you know, she's a good scientist. So what she did is she tried to come up with predictions for this. And one of the predictions is that, you know, as the Earth sort of is orbiting the galaxy, eventually it'll pass through this disk, and that'll perturb asteroids that are far away. And then one piece of evidence that, she was claiming for this was periodic extinction events on the Earth. I did not find this particularly compelling, but some people do. So there's a pretty wide range, and absolutely people do postulate things that are totally new forces, or forces that are not what we have, but look very similar to what we have, just only working with dark matter, that type of thing.
Okay, well, that's very interesting. I didn't realize that people were using weak interactions in this fashion. Okay, I'll sort of leave it there and let other people chime in.
This is
Thanks.
Bill Lockman.
Very interesting.
Are you talking about a new set of gauge bosons, or?
So
not?
I don't remember. It was about years ago when this happened. I remember I had just taken a particle physics class at the time, and that was my entire level of expertise with this. But I think so. All I remember is it was the same symmetry group as electromagnetism, and it's been so long since I did that I don't remember.
Okay.
I don't remember enough about that to go through. So I apologize. I think you probably have more expertise in particle physics than I do.
Thank you.
I have a question, Marion Weiler. So based on any preliminary data, I mean, is there any direction that seems to be favored going towards standard dark matter model, or the new one where there's interaction? I mean,
Great question.
Seeing evidence one way or the other, or
yeah, so
just absent evidence?
Absolutely. So now what has happened essentially since I started working in the field, but also my advisor started working in the field 20 years before that, is that a number of problems have been proposed for dark matter. So one of the first and most compelling of these was actually developed by my advisor and his advisor. So these were Anatoly Kvipin and Andrei Krasov, Russian and Ukrainian. What they did is they ran one of the first couple of simulations which was able to actually resolve subhalos. So before this, simulations were not good enough to do it, but Andrei sat down and wrote a really good code, one of the best codes that had ever been written at that point, and it was actually able to do these simulations effectively. And what they saw when they ran this simulation was that they had a huge number of subhalos. They had thousands and thousands of them inside of the dark matter halo. And this was an issue because at the time we only knew about 8 or I think 12 satellite galaxies around the Milky Way. And so they said, this is a problem. And many people interpreted this as evidence against standard dark matter, because standard dark matter was just predicting too many satellites. And it's sort of it has an official name, the missing satellites problem, which is, why are these satellites missing? And eventually it turned out, and you can sort of demonstrate this pretty compellingly, especially with modern simulations, but also with sort of more direct measurements, that the issue was that they were not correctly mapping the dark matter halos in their simulation to stars. So one of the things that we talked about was that as you go to lower and lower mass dark matter halos, you get more and more and more of them. So it's really important, if you want to compare the number of dark matter halos to the number of satellites, that you're matching things up so that the right dark matter halo sort of corresponds to the right amount of stars. And at the times, their simulations couldn't quite do this. And there were sort of other physics that went in there that people often wouldn't account for. And once you do account for that, the predictions match up essentially perfectly. They match up very, very well. And then sort of later, people would bring up another problem, and people were like, all right, this means that standard dark matter is dead. There's no way it's getting out of this one. And then, it turns out that, okay, so we ran higher resolution simulations, and we realized that when new observations of star forming regions came out, that old simulations hadn't been forming stars correctly or something like this, suddenly that problem also gets solved. Now, there's still a couple things that are sort of sitting out there on the peripheral that haven't been solved yet. But historically, we've been going in this direction where every time we are sure that there's no way that standard dark matter can wiggle its way out of something, it wiggles its way out of it. But in general, most of the approaches here try to find out what the inner density of very small galaxies are. So galaxies that have like 100 stars, for example, where you can't imagine that the stars of the galaxy is doing anything to the dark matter. You try to figure out what's happening with that, and you try to see whether or not you can see predictions that are different from standard dark matter. And a lot of the research that we're doing is trying to make it so that you can more compellingly say, all right, this observation that we see is inconsistent with standard dark matter. But I don't think that there's any compelling evidence, sorry, let me rephrase that. I don't think there's any conclusive evidence that points away from standard dark matter yet. There's a lot of evidence that is compelling enough that it can motivate new research in that direction. But I think that standard dark matter still is holding on to its title of standard pretty well.
This is Ken Lem again. On the missing satellite galaxies issue, there's also the issue of whether or not the census of satellite galaxies around the Milky Way is adequately nailed down. And so I guess the Vera Rubin telescope is supposed to explore that further to see if there are satellite galaxies that are just so faint that the prior surveys just have not picked them up yet.
Perfect. And thank you for pointing that out. I forgot to bring that up also. So, you know, at the first time that the missing satellites problem was brought up, we had, 12 satellites that we had measured, had detected. And now we have many, many more than that. I think it's probably close to about 100. I should have checked the number before coming here. But and the reason for that is that we have better telescopes. We're doing more conscious surveys searching for these satellites, and we've gotten better at detecting really, really dim satellites. And that's important because a lot of the satellites that we're looking for are so small that like it's almost weird to call them a galaxy. It might be a galaxy with 1,000 stars in it. It might be a galaxy that's hard to tell apart from just a star cluster. It's something that formed from one cloud that collapsed. Right. And so as you bring up, one of the new telescopes, actually this is a telescope where the camera is being built at Stanford also. I just saw it earlier today. It was gorgeous. Is the Vera Rubin Observatory. And so this is a telescope which aims to take images of the entire sky and to do it repeatedly. And one of the things that this will help us with is identifying more and more of these satellite galaxies. And the more that we can identify, the better that we sort of know how many are actually around the Milky Way. The way that we have to do it now is that we have to guess how sensitive our telescopes are. And well, not really guess, it's much better than that. We have estimates of how accurate our telescopes are at different distances, and we try to correct for this. And when we do that, things look consistent with our simulations, but it would be better to just have a better telescope where these corrections have less of an impact on the things that we're looking at.
Yeah, that's great. Thanks.
Mm-hmm.
Another question I have is just maybe a clarification between these satellite galaxies, which you say could be 100 or 1,000 stars, and then just a star cluster, maybe.
Right.
What's really the difference? Is a star cluster in the galaxy, say it's coming from a single gas cloud? How does that different from a satellite galaxy?
Right.
And are these star clusters just satellite galaxies embedded in their own galaxy?
Yeah, so this is a great question, and I've had a lot of long discussions with people where we struggle to define galaxies. I think that I have a definition that I like a lot, but if you wanted to be conservative, you could just say like at a certain point, once you have few enough stars, you're not really a galaxy anymore. But I think the definition that most people essentially end up using is that a galaxy, a star cluster, or let's start with a star cluster. So a star cluster is something that can form inside of a galaxy, and it forms because there's some individual cloud of molecular hydrogen that ends up collapsing and forming a bunch of stars that are bound together. So that's the formation mechanism for a star cluster. But the way that a galaxy forms is that you have its own dark matter halo, and gas condenses into the center of that dark matter halo and then forms stars. And then the question becomes, can you make observations which can compellingly differentiate between those two ways of forming stars? And if you can, then whatever set of observations tells the difference between those are the things that tell you whether or not something is a star cluster or a galaxy. And usually what that comes down to is looking at how large the velocities of the stars are relative to the stellar mass of those stars. So if you can explain the velocities of those stars with just the stars, it's usually a star cluster. But if you can't, it's usually a galaxy, because in that case, there's a lot of dark matter there that does it.
Okay.
But there's certainly much more nuanced definitions than that.
Yes.
And oftentimes you'll look at things like, for example, the amount of metals that are in these objects. So you can tell things about the times that they formed. Is this a population of stars that formed all at once, or is it more diffuse? But there's certainly a wide range of definitions that you can take on here.
Okay, this sounds like the Pluto issue that we're going to face in the future. Some new definitions as well. Andromeda is no longer a galaxy. It's just a big star cluster or something.
Oh, that would be tragic. I would be so sad. I love Andromeda. It's one of my favorite objects in the universe, to be honest. It's just so gorgeous, and we've learned so much physics from it. If it ever became not a galaxy, I would cry myself to sleep.
Oh my gosh, I don't want that to happen.
Yeah. Does anyone else have a question?
Yeah, this is Mike Ryan. Would you mind explaining whether there's relevance in the characteristics of the dark matter and and how you define it with regard to the life and death of the galaxies that presumably are attached to it as a scaffold?
Right.
I sort of lost the connection somewhere along your talk.
Yeah.
Are they largely separate topics, or is there a distinct effect upon the dark matter as the galaxies age, or vice versa?
Absolutely. And just one thing that I want to note, and I'm going to apologize for this. I've been feeling pretty sick today, and I'm starting to feel a little bit ill. So I might sort of end this after another question or two. I'm sorry. I wanted to stay and answer questions for longer.
No problem. We appreciate very much your indulgence.
Yeah, but I do want to answer this question because I think it's a good one, which is that well, all the questions are good. I shouldn't say it in that way. All these questions I've really loved. So the idea is that when you're just forming a galaxy, there's two ways that the properties of the dark matter usually affect what's happening with a galaxy. So one is that it affects its durability when it is orbiting around another dark matter halo. So if you make the center less dense, for example, then it's easier to get ripped apart by the gravity of that dark matter halo. So what can happen is you could have the same dark matter halos that all form together. They form the galaxies in exactly that way. And then when they fell in towards the center, one model of dark matter destroys those galaxies more quickly. So that's one way that it happens. Then the other way that it happens is if you change the dark matter in other ways, you can just prevent certain small dark matter halos from forming at all. And I'll give you an example of this. So the current model of dark matter is something called, cold dark matter. So this is dark matter that if you were to look in the early universe and you were to look at a little patch of dark matter, all of those dark matter particles would have almost exactly the same velocity. They'd be moving sort of smoothly in one direction. And you wouldn't see what you see in air. So if you pick out a patch of air, you see this velocity dispersion of particles in every direction. And that velocity dispersion is what we refer to as temperature. So when there's no dispersion, when everything's moving together, that's really cold. And if there's a lot of dispersion and things aren't moving together, that's something we consider to be warm or hot. So different models of dark matter can be colder or warmer than one another. So for example, if the dark matter were made entirely out of neutrinos, a particle that we already know about, and we already know is really, really hard to sort of detect, then it would be really hot. And you can sort of show this from sort of the properties of the neutrino. And then there are other things that can be somewhere in between being very cold and very hot. But let's think about what happens if you try to form a dark matter halo out of something that's moving really, really fast. So what happens is there's this concept of escape velocity. So the escape velocity of an object is the velocity that you need to be traveling at to escape it. If you want to shoot off a rocket from the Earth and have it, never come back, you give it enough velocity at the start, enough initial kinetic energy, and it just sort of goes out forever without coming back. And So what happens is, as you make an object smaller, its escape velocity goes down. And eventually, if there's some temperature to the dark matter, your escape velocity can be smaller than the temperature. And at this point, dark matter just won't form that dark matter halo because it can always escape from it. So you'll just never form anything below a particular scale. And so this is one of the most popular, so this became popular as a solution to this missing satellites problem initially. So people said, okay, let's just give the dark matter a temperature and then we won't form all these tiny little satellites, problem solved. And so one of the things that, and of course, the issue that you run into is there's this big sort of trade-off. So one way that you could handle this is by giving the dark matter a temperature and then you don't form all those small satellites. Another way you could handle this is by changing how the dark matter and the galaxies are related to one another. So if you put dimmer and dimmer galaxies in these dark matter halos, then you can also have the same effect. So the question becomes, what sort of tests can you do that differentiate between those two scenarios? And this is one of the reasons why people at Stanford are really interested in the connection between stars and dark matter halos. Because if you know that connection really well, then you can differentiate between those two things. You don't have freedom to just put the connection between the stars and the dark matter in whatever way solves the problem that you see. You want to constrain yourself so you don't have freedom to mess around with those sorts of parameters and just, sort of solve whatever observational problems you have. So that's sort of a big research effort, is to sort of go in that direction.